Hello, I'm Shukai. I'm a student from Northwestern focusing on healthcare operations. Thanks to the service science section for recognizing our paper as a competition finalist. In this video, I will discuss optimizing parallel queues of any scale and its application to equitable liver transplant. This is a joint work with my advisor, Professor Sanjay Mehrotra. And also, this is the third part of our paper series on Markov chain finite approximation. This theory is about using tractable finite state Markov chain to approximate intractable continuous state stochastic system. This approach facilitates approximate performance evaluation and subsequent system optimization. The first two papers established the foundations and focused on performance evaluation. In contrast, this third paper focuses on optimization, solution consistency, and its specific application to transplant queues. As a quick introduction to the motivation, we have a global scarcity of cadaveric livers. This scarcity has led to pronounced allocation disparities, notably in terms of gender, ethnicity, and blood groups. Geographic inequalities have also gained extensive research attention recently. Several operational approaches have been proposed to reduce geographic inequalities. Examples include restricting, expanding neighborhoods, and continuous distribution. These approaches all grapple with a central challenge: how to match liver supply and demand in an equitable way across a large number of patient subpopulations of different characteristics. Particularly, we seek insights into whether the scale of transplant centers and patient mortality risks have an implication in designing an equitable allocation policy. And here is how we model the transplant system. We consider 140 transplant centers, each having multiple waitlists based on patient characteristics. Let's see an instance of a patient waitlist. The patient flow has an arrival intensity of lambda 1. Upon arrival, patients enter a buffer and wait for available livers. During waiting, many patients may die before receiving a liver, and there are many such waitlists. Livers are procured from transplant hospitals, constituting a total liver flow. And these livers are allocated to patient waitlists using specific allocation weights. As an illustration, a liver flow with the rate mu1 is allocated to patient waitlist 1. In our transplant model, each patient waitlist can be viewed as a single server queue. For each waitlist, we define the service time as the duration it takes to receive the liver from the moment of reaching the top of the waitlist. Patient's time is the maximum time that a patient can survive without a transplant. And the patient inter-arrival time is the duration between two consecutive patient arrivals. When a patient dies before receiving a liver, we call it an abandonment. Based on exploratory analysis of transplant data, we found that liver flow follows a Poisson process. Therefore, the service time at each waitlist follows an exponential distribution. We also found that patient inter-arrival times do not follow exponential distributions. Now we can view each waitlist as a GI-MI 1 plus GIQ. The first GI means a general inter-arrival time distribution. And the MI means exponential service time distribution. 1 means a single server. Here, donor livers are treated as coming from a virtual server, whose service is to receive donor liver and give it to the first patient on the top of the waitlist. The last GI means the patient customer may abandon or die before a random amount of a patient's time following a general distribution. Abandonment may occur until the service is accomplished, and the patient customers follow first come, first serve rule. For each wait list, the service rate represents the lever allocation rate. Now, since the service rate represents the lever allocation rate, our decision variable is the vector of service rates at each wait list. And each wait list is characterized by an individual intensity lambda and a patient's time distribution j. Our goal is to investigate how these two fundamental characteristics indicate an optimal allocation scheme. And we employ a general and flexible optimization modeling framework. This is important because the selection of objective and constraint functions often depend on the context. Our general optimization model allows for a wide range of steady-state performance measures of patient wait lists. This problem poses significant challenges. First of all, the queuing system's performance is intractable, and the objective and constraints are implicit functions of the service rates. As a result, calculating the derivative is impossible, and optimization is hard. To address this issue, literature often resorts to asymptotic methods, for example, using fluid approximation. By assuming the arrival and the service rates both approaching infinity, the original stochastic queuing system will degenerate into a deterministic fluid model. And this approach is widely used by queuing literature. However, for transplant queues, asymptotic methods may not be reliable. One major reason is that many transplant queues are small scale, and patient arrival intensities are not large enough. And for equity concern, these small transplant centers cannot be excluded from our analysis. Furthermore, very limited literature analyzes the error introduced by asymptotic analysis in a transplant setting, and their reliability is not well understood. Therefore, a more sophisticated analysis approach is needed. So how do we solve this problem? And we use approximation methods. I make this table to compare the original optimization model and our approximation model. In the original model, each wait list is a queue. We approximate the queue with a finite state Markov chain. In the original model, stationary distributions and performance measures are intractable, but they can be easily obtained for a finite state Markov chain. Originally, the objective and constraint functions are stochastic, non-convex, and implicit functions of service rates. We approximate them with piecewise linear functions. In this way, the original lever allocation problem, which is a non-convex stochastic program with implicit constraints, is now approximately solved as a deterministic piecewise linear program. And our approximate solutions have theoretical guarantees. Under mild assumptions, our approximate solution is near optimal. And as we increase the order of approximation, the optimality gap disappears. And we conduct numerical experiments to test our methods. We use national data. Through exploratory analysis, we found that a majority of patient wait lists have small arrival intensities and do not satisfy the large market assumption required by asymptotic analysis. Then we evaluated this transplant queue's performance. We compare our method with fluid queues. We found that our method is 100 times more accurate than the fluid approximation. And we respectively use our approximation method and a fluid model to derive optimal lever allocation schemes. We found that allocation scheme derived by our method increases resource utilization and allocation equity compared with that derived by a fluid model. In addition, we found that appropriately increasing the proportion of levers allocated to wait lists with small scales or high mortality risks improves the allocation equity. Now we make concluding remarks. We model patient waitlist as a non-fluid queue, which are proven to be more accurate than the widely used fluid models in transplant literature. And to evaluate and optimize the system performance, we use a finite state Markov chain to approximate the original continuous state stochastic system. Our approximation has computable error bounds, and it does not require a large system scale. And we further formulated the lever allocation problem into a capacity sizing problem that optimizes the service rates for multiple queues. And our optimization model allows for flexible objectives and constraint functions so that it can fit into different application contexts. By leveraging our approximate performance evaluation approach and the piecewise linear approximation, we are able to derive a formula-based algorithm that guarantees a near-optimal solution. Through numerical experiments, we found that a greater allocation of livers to small transplant centers and those with vulnerable populations can improve the allocation equity. Last but not least, although our motivation is from liver allocation, the solution approach developed in this paper can be applied in other operational contexts with similar modeling frameworks. And that's the end of my slides. Thank you for watching.